Hi, this is Steve Karam, the Oracle Alchemist. I've spent the last few days making a tutorial about calculating term frequency inverse document frequency, otherwise known as TF-IDF, and I've been doing it using Hadoop Streaming with Bash scripts. Hadoop Streaming is a way that you can write Hadoop MapReduce jobs without having to know any Java. Instead, you can use any language that supports standard in or standard out. So for instance, Perl, PHP, Bash, which I used, JavaScript with Node.js, or the ever-popular Python and many others. If you haven't seen the work that I've been doing with that, you can find the articles on oraclealchemist.com, and I'll also include a link in the description of the video. So calculating TF-IDF was a three-part exercise. There was a MapReduce job to calculate term frequency. There was a MapReduce job to calculate document frequency, and then a final job to calculate TF-IDF. And just so you know, so TF-IDF it's an important algorithm in the world of text analytics. Basically what it allows you to do is it allows you to score documents to see, and words, to see how important a word is to a document in relation to the entire collection of documents, or corpus as it's called. So to calculate that, you need the term frequency. The term frequency is going to be how often a term appears inside of a document, each document in your collection. Document frequency is the next piece, and you need that, which tells you how many documents a word appears in. And then finally, you use those to calculate the term frequency inverse document frequency, which will give you a nice set score per word document combo, and it will tell you how important that term is to that document and to the set of documents as a whole. So as I mentioned, I made a set of bash scripts that went ahead and calculated that. It required 3 MapReduce jobs. And what we're going to do now is we're going to create a workflow with Oozie using Hue. Hue is a popular web interface for Hadoop, and you can see it right here. And Oozie is a workflow editor, which makes it easy to execute concurrent, or not concurrent, but sequential or forked MapReduce tasks. So once the workflow is created, we're going to submit it as a job. We're going to watch it create the final output, and then we're going to load the query into Hive. We're going to load the output into Hive, and we're going to use SQL to query it once it's completed. So let's get started. So what we've got here is the Hue dashboard, and the Hue dashboard has a ton of great components. It's a good web UI. It includes Beeswax, which is a Hive UI. It has a file browser, a job designer, Oozie editor and dashboard, which we'll be using, the Hue shell, which has tools like Grunt, which is a tool for Pig, where you can write Pig Latin scripts that can be used to as the equivalent to MapReduce jobs, and then just the regular other meta stuff. So Oozie is what we're going to be using here. Before we get onto that, I want to show a little bit. We're not going to recap my 3 days of blog articles. You can read those yourself. But what I do want to do is just show where we are right now. So in my working directory, we have, first of all, a directory called Crane. And if I go to the Crane directory, you see that I have 8 text files. Now each of these files, they're very small. I'm doing this on a virtual machine on a MacBook Air, so I didn't want to do too big of a job. Each of these text files contains a separate poem by my favorite poet. His name is Stephen Crane. So for instance, if I cat a man said to the universe, a man said to the universe, "Sir, I exist. However," replied the universe, "the fact has not created in me a sense of obligation." Very simple, plain text, line for line, some characters in there and such, but mostly just words and spaces. And this is going to be perfect for text parsing. We don't have to do anything funky to try to convert it. We're not trying to work with PDFs or docs, which Hadoop can do, but this is a simple bash script, so we're going to make it easy. So that's the Crane folder, and this folder has already been loaded into Hadoop, into HDFS. You can see that with this command. Hadoop fs-ls user training. You can see there's a folder here called Crane, And if I look in there, there's all my files. All right, so I'm already loaded into HDFS, ready to go. The other thing that I have in here are a bunch of shell scripts, and these are the shell scripts that I'm going to be using to run my MapReduce jobs. We have map and red TF.sh, that's the map job and the reduce job for term frequency. We have mapdf and reddf.sh, that is to map the document frequency and to reduce the document frequency. And then we have map TF-IDF.sh, which is the final mapper. This final map job is going to take all of the term frequency and the document frequency, and it's going to run through the algorithm that is required to calculate TF-IDF. That algorithm, as you can see here, is a multiplication to a logarithm of a couple different variables. We'll get to that, and it's covered in detail in my blog. On the blog articles where I have the 3 days of MapReduce jobs, I go through each line of each piece of this code one by one. So it's definitely beneficial if you want to see how this is actually working to read those. For now, we're going to concern ourselves with Oozie and Hive and not worry about the actual parts in the background too much anyways. So just so you know, also before I move on to the Oozie part, we're doing all of this against the Cloudera VM. The Cloudera Quick Start VM is awesome, and I'm actually using the training VM. It's pretty much the same thing though. Both of these, and this is it right here, you can download it for VMware VirtualBox KVM. They come with an astounding amount of software. You get a fully configured Hadoop environment with HDFS, name node and data node configured for pseudo distribution. You get Hive, Hue, Oozie, Pig, you get HBase, Zookeeper, various other programs, and of course Cloudera Manager, which is an excellent management software for Hadoop. You also can experiment with both the old and new MapReduce APIs and MapReduce v1 and v2, the Yarn-enabled MapReduce. So you have both of those options. While I'm showing you this, and like I said, it's a great resource. It's absolutely astounding and it's free. So definitely if you want to get into Hadoop, you should download it. While I'm showing you this though, one of the big things I want to make you aware of is to run Hadoop streaming jobs. Again, those are those jobs that don't use Java. They use standard in, standard out. To run Hadoop streaming jobs, you need, through Oozie, you are going to need to load the sharelib. The sharelib is a group of shared libraries that include jar files, including the one used for Hadoop streaming. If you don't load these in, you're going to have a serious pain in the neck on your hands. You're going to have to reference these files every single run, add them to your deployment directories, real pain. Instead, you're going to want to do these steps. Now, I'm not going to go through these, I've already done them, but I will provide the link to this page in the YouTube description and on my blog so that you are able to follow these steps on your own to install Oozie Sharelib and Hadoop HDFS for the Oozie user home directory. So, that being said, let's get to the main event. So right here, what I'm in is the Oozie dashboard. And you can see here, it's nothing fancy, but I can see running jobs, I can see completed jobs. You can see I've run through this a few times. We'll be going through the whole thing from scratch, nothing edited, we're going to start from scratch. So what I've got is the dashboard, I've got workflows, which I have none right now. A workflow is a set of actions that make up an Oozie job. So, for instance, an action to map, reduce something, and then an action to run a command or load some data or use Scoop to take data from Oracle or MySQL and put it into HDFS. You can do pretty much anything in these workflows. Coordinators you can use to schedule components. You can use them to create actions or create things that happen when a job completes. We can create forks and various other things. And then history, so you can see the history of everything you've done. So let's go ahead and create our workflow. What I'm going to do is I'm going to go to the workflow editor here, and the first thing I'm going to do is just click create. And we're going to call this workflow Crane TF-IDF. because the whole goal of the workflow is to calculate the TF-IDF of these Stephen Crane documents. And we are going to say that this is a TF-IDF calculation on the works of Stephen Crane. Simple enough. And we're ready to build our flow. So before we get on to the actual adding of actions, there's one important thing that we're going to need to do. We need to go to Properties for the workflow itself. We need to click on Advanced. And we need to add a parameter. You can see here the basic settings. We need to add a parameter that's required to use those shared libraries that I mentioned earlier. We're going to add a name of Oozie.use.system.libpath and set that to true. And that will tell Oozie to use those shared libs, which are going to allow it to do Hadoop streaming. If you're writing pure Java MapReduce jobs, you probably don't need to do this. I'm not 100% on that, but for streaming, you definitely do. Also, if you're going to write jobs via pipes for C++, you have to do it there too. So I'm going to save. I'm good. I'm ready to create my flow. So we're going to start, if you look on the left, the kind of actions you can add. We can add MapReduce jobs. We can add streaming, Java, Pig, Hive, Scoop, Shell, SSH. You can pretty much do whatever you want. Even if what you want to do is not on the list, if you can call it via Shell, then it's on the list. So for instance, if you want to add a Mahout job to this, even though that's not there, you could always call it manually from within your flow and in any particular action. Because we're doing Hadoop streaming, we're going to go ahead and add a streaming action. Now we are going to call this action calc TF, because all we're doing in this particular part is calculating the term frequency. This is the first part of the job. You can see here that it can include a mapper, it can include a reducer. We're going to do the first job. Calculate TF. Step 1 is the description. The mapper is going to be the mapper that I have here on the host. So it's going to be home training Steve maptf.sh. The reducer will be home training Steve redtf.sh. Now as far as properties, there's definitely two properties we're going to need for almost every action we do here. The first property is mapred.input.dir, and that's going to be the directory that will serve as the input for our job. So I want this data to come from the HDFS location user training crane. That is where I loaded those TXT files. This is in HDFS. Now remember, the mapper and the reducer, these are on your local file system. These properties are in HDFS. It's a very important distinction because otherwise your Oozie job won't work. One other parameter that we're going to need to add is mapred output dir. This is where I want the data to go when it's all done. So once I map and once I reduce, where does the output go? And I want that to go to the HDFS location user training crane project TF. Now just so you know, this destination, just like anything else in Hadoop, cannot exist. It will not overwrite directories. You must have a non-existent location. In our case, Crane project doesn't exist and TF doesn't exist, so we're good to go. Now you may notice for both of these I used mapred dot. If you know MapReduce, you know that that is the old API for MapReduce, which makes use of the mapred org.apache.hadoop.mapred. We are using that because from what I understand, Hadoop Streaming only supports the old API. The new API would use MapReduce instead of MapRed. But anyways, it doesn't matter, it works for us. One more property I need to add, and this is a caveat of Hadoop Streaming. Stream.num.map.output.key.fields is 2. And the reason I need to add that is because Hadoop Streaming does not keep track of key state the same way that Java does. When you write a MapReduce job in Java, you're able to define whatever kind of input and output formats you want. And those can be records that consist of 10 different values to make up one key. It doesn't matter. In Hadoop Streaming, we're working off of standard in and standard out. Hadoop has no way to know which column or combination of columns makes our key. So if you have more than one column making up your key, you need to set this here. And we did the same thing in the blog. If you would like a more detailed reasoning for this, you can look at day 1 where we calculated a TF at the command line. So these are the only properties we need to go ahead and run the data that's in user training crane through my mapper, through my reducer, and output to crane project/TF. So now I'm going to go ahead and click Save. And I have my first action underneath the crane TF-IDF workflow. You can see here that it's called calc-TF. It is a streaming action, and it shows the description there. Now you can click on this pretty much anywhere to edit it. We'll get to that in a moment. I could go ahead right now and click on streaming and do another one and add all the stuff manually, but I'm lazy, and that's all right, nothing wrong with that. So instead I'm going to click this little button which makes a copy of it. And you see here it created calc-TF copy. I can click on that anywhere and edit it. I'm going to call this one calc-DF for document frequency, change the description. I'm going to change my mapper to be mapdf.sh, my reducer to be reddf.sh, and I'm going to take a look at my job properties. Now on these, the input of the document frequency is not going to be crane, it's actually going to be the output of the last job. So it runs through the TF, outputs the data into crane project/TF. This one will take from crane project/TF and write to crane project/DF. So it's going to take the final output of that last part of the workflow and it's going to use that as input and then output to user training crane project/DF sitting on HDFS. Now the only other major difference is that this second part only has one key column. It does not have two. The document frequency algorithm only has a key of term, and this is explained in the blog article for day 2 if you want to check that out if you haven't seen it yet. So this is all we need to change. We change the mapper, the reducer, our input and output directories, and the stream num map output key fields. Once we're sure we're good, I click Save, and we now have our second step. So the third step, same thing. This step is going to be for the final TF-IDF calculation. This workflow has 3 components. So I'm going to name this calc TF-IDF, calculate TF-IDF step 3. We're going to change the mapper to maptfidf.sh, and for the reducer, the TF-IDF portion doesn't use any kind of special aggregating reducer. It actually uses this one. It's called an identity reducer. That is a reducer that basically takes in whatever's given to it and spits it right back out. Now, if you're wondering what the purpose behind that is, it's actually pretty simple. When data goes from mappers to reducers, it comes in sorted. So this will give us our nice output sent to the reducer and sorted, ready to go. Now that's with one reducer. In this case we have one, in some cases you may not have that. But still what it gives you is also a reduced number of outputs. If there's 8 files coming into my source job, then you've got 8 mappers. When you have an identity reducer, it can come out with that single reducer's output. Makes it nice and clean. So for this job here, the mapper is maptfidf.sh. The reducer is identityreducer.sh. The input will be the user training crane project DF location. We'll make the output user training crane project TFIDF, the final one. And for this one, our number of key fields coming out of the mapper is actually 2, not 1. We have to add one additional property. Sad to say, I have to cheat on this one. This one's going to be called n, and it's going to have a value of 8. The reason that we need to have this property is because in this script, one of the things you need for the calculation of TF-IDF is the number of documents that you're actually running against. And it's very easy to find. In my scripting, I actually used an ls command with a word count. It's a pretty simple MapReduce in itself. I could have run a MapReduce to do that, but that would have been a tremendous waste of resources. There's no point in wasting your cluster resources to do what a simple ls command can do. Since you're going to be using glob matching to identify your input anyways, you may as well use a variable and just set it yourself. It'll save a lot of time. So for the final calculation, we have a map TF-IDF.sh, we have an identity reducer, we have the input directory as the df, the output directory as TF-IDF, we have 2 fields in the key coming out of the mapper, and an n value, which is the total number of documents, is 8. And we are done, and we can click Save. So now we have all 3 of our steps. We calculate term frequency, we calculate document frequency, we calculate the final TF-IDF. Everything is set to go. So we're going to go ahead and go back to the workflows area where you can see our job there. You can see the name and description. Sorry, the date's all off. And you can see that this has 3 steps to it. I'm going to select this item and click Submit. It wants to verify my job parameter, and absolutely I want that, or else streaming would not work. And you can see the workflow was submitted. It actually shows here, you can see the workflow, you can see information about it and that it's running, some basic metadata. You can kill it if you want to, definitely don't want to do that. I'm going to click refresh so you can see how this thing updates. You can see that it shows it's at 50% and it's actually in the middle of the calculate TF portion. Now while it's doing that, we can look at some of this other stuff here. You can click on actions to see the different actions that have been taken, if there's been any errors, retries, etc. We can look at the various job details and configuration. We can look at the plain text log, which is very useful. And the actual Oozie definition. Now this GUI is all well and good, but in many cases this XML file is what you will be using to define your Oozie workflows. It's used at the command line and it makes it very simple to edit or do whatever you want with them. So let's go back, click on Graph, and refresh again. You can see we're at 75% now. The first MapReduce job is completed. The second MapReduce job is completed, and it's currently working on the third. Now another thing you can do here on this page is you can click on each of the individual steps. Right now, for instance, this one here, the status is okay. Hey, status succeeded, it finished by the time I clicked. The cool part is you can click here on the job itself and you can see every bit of the components that made up that task. You can see each phase of the map, the setup, the map, the cleanup. You can see the reduce portion. You can click on any of these and see how their status went and if they had any problems and when various pieces finished. You can see metadata related to the job. It's absolutely great to be able to log your information. Hadoop logs a ton of good info, and you can see it all right here. So we're going to go back to Oozie. You can see that my job succeeded, and let's just verify that. We can do that at the command line. There's nothing special that happens when it succeeds. You don't get a big flash on the screen or pretty graphs or anything like that. What we can do, however, is take a look at Crane Project /TFIDF, the expected output of the whole job. And you can see here that there's 3 files, success, logs, and part-00000, which is our final output. Now if I do a Hadoop fs-cat on that file, there's my final output. Tab delimited, term, file, TF-IDF score. using the algorithm that I had created. All the intermediate data is still there as well. So for instance, I can take a look at crane project /df/part. And here was the second step where it calculated the document frequency. You can see the word, the file, the term frequency, and the document frequency. Those were what I used as inputs to the final job to actually figure out the TF-IDF score with the algorithm. So our job completed, it was successful. Oozie did a great job. We are able to define workflows, create whatever we want, and we get our final output where it's expected. We didn't have to run 3 separate Hadoop commands. It all did it for us. And you can put that on schedulers. You could have Flume, for instance. Flume is like a tail-f on steroids for Hadoop. It takes data from multiple sources and it brings it in as it changes into HDFS. So you could have Flume reading web logs from your various application servers and then have a scheduled Oozie workflow that goes through that, crunches it, and does whatever you need. So now that we're done with Oozie, we've got our final output. Instead of just looking at it like this on a big empty slate, let's go ahead and use Hive and actually run a SQL query against it. So we click on Hive and we see here that it comes to a Hive query screen. Something like this would look familiar to any Oracle developer or anything like that. We're going to click on Tables on the right here and say that we want to create a new table from a file. This new table, we will call it Crane TFIDF. The description we'll just leave empty. For the input file, we can browse the HDFS file system, and you can see that in User Training Crane Project TFIDF, there is my part file. And then you can see here that it's asking us, do you want to import the data? Now what this does, when you say yes to that, is it takes that part 00000 file and it brings it into the Hive metastore and it keeps the data in there. Now you can uncheck this and use what's called an external table. Little different, we're not going to mess with that. We're going to go ahead and let it do what it wants to do. So I'm going to say OK and click Next. And now it's asking us to choose our delimiter. It automatically figured out that it was tab delimited, but you can use all kinds of different options or whatever you want if you want to go with other. You can take a look at the preview here and see that it's nicely delimited. This is what I would expect. Word, file, and then the TF-IDF score. Now we're going to give our columns names. This one will be Word. Column 2 will be File. Column 3 will be TF-IDF, and we will make that of data type float. It's not a string. We want to be able to do numerical calculations on it. That's the whole point of algorithms in the first place. And we click Create Table. Now you see here the syntax that it used for the DDL. Here is the job log as it's creating this object, and here's our final table. File, TF-IDF, and Word. You can click Browse Data. Here's the job that it submitted to do so. And here's our data that comes back to us. Row number, words, files, and scores. You can download those as a CSV. You can download them as XLS, whatever you want to do. Now I choose, as an Oracle lover, to query them. So I'm going to click on Query Editor and write a query. And we are going to get the data back with a SQL query. Now, before I do that, just so you know, Hive does not have the most advanced of SQL engines. You can do joins, which is great because joining via MapReduce is a pain, but you have to use ANSI syntax for the joins. That's okay for most people. You can use things like group by and order by, which is good. You're going to need to do aggregations after all. You can use inline views, but not in the where clause. You can only use those in the from clause, which is somewhat limiting. And you can't use things like minus and intersect and stuff like that. But SQL wasn't born in a day, so this stuff will come. For right now, we're going to do a relatively simple query. Select File, TF-IDF, from Crane TF-IDF, where Word equals U, order by TF-IDF descending. So for instance, if someone decided to make a search engine of the complete works of Stephen Crane, they could use this query, to come back, you say someone searched for the word you. It would look for all of the documents containing the word you, and then it would order them descending by their TF-IDF score. Remember that TF-IDF is a measure of how important a word is relative to a document and to the corpus or collection of documents. So the higher the score, the more relevant. So a word like you, for instance, might be in all of them, it might be in only one of them, and then the score will be different based on that. So now that I've got my query, I'm going to click execute. There's the job log of while it goes ahead and does this. This will take a moment. Hive is not the fastest engine in the world. If you're interested in lightning fast query engine, I would suggest you look into Impala. Impala is a Cloudera software. It runs on top of HDFS, and it is very, very fast. So you can see here my query came back with results. I got back 2 files that contain the word you. One is called pursuing the horizon.txt. The other one is metaseer.txt. And you may notice that both of those came back, the TF-IDF score for this one is higher than this one. That would indicate that pursuing the horizon is more relevant to my search than metaseer. So, first, before we move on, Hive worked. We were able to create a table out of our Oozie workflow results. We were able to run this script, and we were able to get back our scores. Now remember, Hive is also an action possibility in Oozie, which means we could have automated the creation of Hive tables right there inside of Oozie. It's incredibly extensible. So now that we see these results, let's just take a final look and figure out why is pursuing the horizon, why does that have a higher TF-IDF score than metaseer? So to do that, we're going to go to the file browser. I can use my commands, but let's just take a look at this. Here's Crane project and the TF-IDF directory. Actually, I'm sorry, we're supposed to be looking at the source. Let's look at Crane. So the 2 files were Pursuing the Horizon and metaseer. Pursuing the Horizon had a higher TF-IDF score. I saw a man pursuing the horizon. Round and round they sped. I was disturbed at this. I accosted the man. It is futile, I said. You can never. You lie, he cried, and ran on. It sounds like a lot of people receiving advice sometimes, even from experts. Anyways, beyond the point. If you look at this, you've got the word you here and the word you here. The word you shows up twice in this document. Now the other document, metaseer, I'm not going to read the whole thing to you. It's a little longer, but again, very good. I love Stephen Crane. If I scan through this, I can see that the word you only shows up once. So you is visible in both documents. It should definitely be viewed in a search engine. Both documents should be seen. But the other one, it's more important because the word appears more times. Now there's other ways you want to measure this. This is not the only measure of a search engine. If it was, Google wouldn't have much of a domination. You also can look at things like word co-occurrence and percentages and saturation. You can look at various components to figure out what piece of text is more important than what other piece of text. This was a basic way of looking at it, which still is very cool. It uses a very well-known calculation. We were able to do that in Bash scripting using Hadoop Streaming, scheduled via Oozie, managed via Hive, and then queried via Hive. Definitely a cool ecosystem. Oh, and all of this was done on the Cloudera virtual machine running inside my MacBook Air. So very powerful stuff. Anyone can do this. Please check out my blog. It has great information on how I got through these steps, what each shell script contains, and how I did all of them, including the testing. You can see it all there. So hopefully this was helpful to many of you, and till next time.